but we want to actually, not the T-form points, we want to go to the new image points as characterized by this IMREF2D. And there is a routine that will calculate that for you. And it's called World2 Intrinsic. And you specify the reference parameters, and you specify the world points, which are the ones we got up there, and it will give you what it calls X intrinsic, Y intrinsic. And for the life of me, I have no idea why it's called intrinsic. I don't know what's intrinsic about it. This is just, the MATLAB documentation. Okay, so transform points forward, do the world to intrinsic, and then we can overlay that on the transformed image, which will produce there it is. Okay, so if we look at that, there's the lines going along the hallway. They look pretty parallel. Here's the checkerboard zoomed in on. And if you look at that, you can see where I missed it a little bit, right? But it's a little bit more exaggerated when seen from this point of view, right? But nonetheless, it's there. So this is, if anything, just reinforcing that the bottom of the camera is indeed, has a place, there's a place in the world for that, all right? So. Okay, now, if the target board is based on 24 inches, the world points were used in the calculating the transform. So things ought to be in units of inches. All right? We have to divide by 12 if we're going to convert to feet. So what we can do is we can look at the distance 0, 24. That's going to go 24 inches across. And I'm going to make it at a y value of 0. Right? And then I'm going to take those world coordinates and I'm going to convert them to intrinsic coordinates. And I'm going to rely on the fact that the checkerboard, because of the T-form, is aligned with the x-axis. So all I have to do is to subtract the two x positions, and that should be 24 inches worth of distance. Okay? So if I take that target width and divide it by 2 feet, all right, that's going to give me, here's the number of pixels per 2 feet. Divided by 2 will give me the number of pixels per foot. So this is coming out 48 pixels per foot. Okay, now we can look at the hallway. Remember, I did the two lines along the hallway, and they're coming out pretty, I mean, because the checkerboard seems to be pretty well aligned to that, they're coming out, you know, I think they're pretty vertical. So I can take the x value here, subtract it from the x value there, and I can take the x value here, subtract it from the x value there, or any combination of them, and I should get, and then I can, this is the one we're looking at. Okay, so I can subtract those two, and I can divide by the scale that I determined earlier, which is 48 pixels per foot, and then get the number of feet across the hallway. So we run that section. And that comes out just a shade shy of 6 feet. Right? And we measured it at being approximately 6 feet when we measured that hallway. I don't know if we were careful enough to get it within a tenth of, you know, within an inch or so, but at least it's coming out approximately what we would expect. And finally, out of curiosity, we can look at the slope of the baseline, which is kind of the angle between the base of the camera and the base of the checkerboard. And here we're choosing, or I'm choosing to do a arctangent. And I'm coming up with about 3 degrees as the angle between the camera base and the checkerboard base that we saw was tilted, right? And this is saying, yeah, it's tilted to about a 3-degree angle, okay? Now, when we took the second picture, I moved the camera, but I did not change the position of the camera. I didn't tilt it down. I just slid it over and looked down the other hallway. Right? So, as long as I've done that, the T-form from the first image should be valid for the second image, because the downward angle of the camera is about the same. Okay, so I'm going to use exactly the same T-form for the second image as I did for the first image. Okay, so there's the checkerboard points. Remember, this is Peugeot calibrator. Let me show you how badly it did with the corner positions. So, not so good. Luckily, we're not going to use them. Okay, instead we're going to use the same T-form that we did from the first image and change the reference a little bit. And we get that. think I ran out of time right about here, but what can we do? Well, this is the default command. It looks like around 400 pixels across the hallway. And maybe 100 across the checkerboard. So 100 pixels is 2 feet. So that's 50 pixels per foot, right? And it's about 400 pixels across, which makes the hallway about 8 feet wide, approximately. Which is, I think, we measured that, and that's about what it is. This hallway is about 8 feet wide. That other hallway is about 6 feet wide. Hard to tell if how perfect this is. I could see, hard to see here. Question is whether here's the edge of the hallway, at least as much as I can. Well, I can see a little bit up there too. Here is the edge of the hallway along there. I don't know, it might be diverging just a tiny little bit there. So from moving the camera from one place to another, may have disturbed things a little bit. Or even pushing the shutter because the tripod is not perfectly aligned. Okay, any questions there? With any luck, that should be of some help when you're working on the homework assignment. Okay, forget about that target here. Let's concentrate on the image. So here's a point out in space. Here's two cameras. Okay? So this camera is producing an image at that point, and this point is producing an image right here. And if we look at the, that hardly looks like the center of the image. Now I take it back. I think this point is, okay, yeah, this point is hitting the image here, but it's proceeding on to the, it's directed at the center of the camera here. And same thing here, this is directed here. Point 2 is not on the image, it's behind the image, on focal length. All right, so if we take the center of this camera and draw a line to the center of that camera, what that is the center of camera 1 as seen by camera 2. And then over here, this point where it intersects the camera, this is the center of camera 2 as seen by camera 1. It's the same line, right? It has to be the same line, right? But that line is called the epipolar line. All right? It just depends on the any two cameras. You can take the center of one to the first image, the center of the second to the second image. At least you can calculate that, because you don't really know where the camera center is, only in the So that line and these two lines turn out to define a plane, okay, called the epipolar plane for that data point. So this point, and that point define a plane, and this line is in the same plane. Look at it that way. Okay? All right, so we have epipoles, we have epipolar line, and we have the two images as seen by the camera. Cameras happen to be looking at the same point, but that's not going to be required. Okay, 3D line, we can find distance from point to line, we've done that. Let's back up to here again. When we look at the images, all we really know is we know where this point is. It's the image in camera 1. And we know where that point is. That's the image in camera 2. And we know that the point in question lies somewhere along this vector, but we don't know where. Right? We do know it lies along that vector. And we know that the point in space lies along this vector. So if we want to find out where that point is from two images, we can triangulate those two vectors and see where they intersect. Are they going to intersect perfectly in the real world? No, because when you look at the point on the camera, there's distortion and there is error in determining exactly the image coordinates of the point, you know, so it's not going to be perfect. So we have to be prepared if you do instead of expecting it to intersect, we're back to the same thing we did with our vanishing points. All we can look for is the point of closest approach, which hopefully is 0, right? But in real life, it won't be. Okay, so here is our back projection equations. If they are parallel, there's no, you know, there's a 0 determinant in there and no unique solution. Okay, here we happen to know where the point is. We're going through the calculation of the position of the intersection point, and we're calculating where the point is. Can't really tell from here. All right, there's that. So here we are doing, this script is doing the calculations that we showed in the